Let me tell you something that might genuinely shock you. Every physicist working on gravity, every cosmologist studying the origins of the universe, every string theorist, including me, has at some point lost sleep over a single question. Not what happened before the Big Bang, not are there other universes. The question is this: when something falls into a black hole, is the information about what it was, its composition, its history, its quantum state, destroyed forever? And if it is, then one of the most fundamental principles in all of physics is wrong. Not just a little wrong, catastrophically wrong. I'm Leonard Susskind. I've been a theoretical physicist for more than 50 years, most of that time at Stanford. I helped develop string theory, I came up with the holographic principle, and I spent the better part of 2 decades fighting, and I do mean fighting, with Stephen Hawking over exactly this question. Stephen said information was destroyed. I said it wasn't. Let me tell you why I think physics is on my side, and let me be precise about this. First, let's be clear about what we mean by information in physics. I'm not talking about the kind of information stored on your hard drive, though that's part of it. I'm talking about something much deeper. In quantum mechanics, the complete description of any system, every particle, every field, every interaction, is encoded in what we call the quantum state, the wave function. And there's a principle baked into the foundations of quantum mechanics since the 1920s that says the evolution of this quantum state is unitary. That's a technical word, but what it means in plain language is this: the laws of physics are reversible. If you know the state of a system at any given time, you can in principle reconstruct its state at any earlier time. Nothing is lost, nothing is erased. Information is conserved the same way energy is conserved. This isn't a minor assumption, this is the bedrock. Unitarity, the conservation of quantum information, underlies everything we know about quantum field theory, about the standard model of particle physics, about every successful prediction we've made in the last 100 years. If unitarity fails, the whole structure of physics develops cracks, deep structural cracks. Now here's where black holes come in and make everything difficult. In 1915, Einstein published his general theory of relativity, and within a year, Carl Schwarzschild solved Einstein's equations for a spherically symmetric mass. What he found was extraordinary. If you compress enough mass into a small enough region, the curvature of space-time becomes so extreme that nothing, not light, not any signal, can escape. The boundary of this region is called the event horizon. Once you cross it, you're gone. From the perspective of someone outside, you've fallen off the edge of the knowable universe. For decades, black holes were theoretical curiosities. Then in the 1960s and 70s, people like Roger Penrose and Stephen Hawking showed that black holes were inevitable consequences of gravitational collapse. Real stars, when they exhaust their nuclear fuel, really do form black holes. We've now observed them directly. The Event Horizon Telescope imaged the shadow of the black hole at the center of galaxy M87 in 2019. About 6.5 billion solar masses, a dark region roughly 40 billion kilometers across. That's not a typo, 40 billion kilometers. But the real trouble started in 1974, when Stephen Hawking made one of the most beautiful and disturbing discoveries in 20th century physics. He showed that black holes aren't perfectly black. They radiate, they glow, they emit particles, photons, neutrinos, gravitons, with a thermal spectrum like a hot coal. The temperature of this radiation is inversely proportional to the mass of the black hole. For a black hole the mass of our sun, the temperature is about 60 billionths of a Kelvin, 6 × 10⁻⁸ Kelvin. Absurdly cold, far colder than the cosmic microwave background at 2.7 Kelvin, which means such a black hole actually absorbs more radiation than it emits. But the principle is there. Black holes radiate. And here's the really disturbing part. If a black hole radiates, it loses energy. If it loses energy, it loses mass. E equals mc squared tells you mass and energy are the same thing. If it loses mass, it shrinks. If it shrinks, it gets hotter. If it gets hotter, it radiates faster. This is a runaway process. Given enough time, a black hole evaporates completely. A black hole the mass of our sun would take about 10 to the 67th years to evaporate, far longer than the current age of the universe, which is about 13.8 billion years. But a small enough black hole, say one formed in the early universe with a mass of about 10 to the 11th kilograms, roughly the mass of a small mountain, would be evaporating right now. And at the very end, in the last fraction of a second, it would release a burst of energy equivalent to about 1 million megaton nuclear weapons. Now here's the question that kept me and Stephen arguing for 25 years. When the black hole evaporates, what happens to the information about everything that fell in? Suppose you throw an encyclopedia into a black hole. You throw in a grand piano. You throw in a cat. The black hole grows a little each time. Then it radiates. And when you analyze Hawking radiation the way Hawking originally did it, the radiation looks perfectly thermal, random, featureless. It contains no more information about what fell in than the glow of a hot iron tells you about the history of the ore it was smelted from. If that's true, the information is gone, destroyed, and unitarity is violated. Hawking embraced this conclusion. He said, in effect, that black holes are where quantum mechanics breaks down. Information goes in, and pure randomness comes out. He was very confident about this. He even made a bet with me and John Preskill in 1997, a bet he later conceded, to his credit, in 2004. But let me show you why I was never comfortable with Hawking's conclusion and why I think the physics ultimately vindicates unitarity. The first clue comes from thermodynamics. In 1972, Jacob Bekenstein, then a graduate student of John Wheeler, proposed that black holes have entropy. Not just a little entropy, an enormous amount of entropy, proportional to the area of the event horizon. Hawking later made this precise. The entropy of a black hole is given by the Bekenstein-Hawking formula, S equals A over 4, where A is the area of the horizon measured in Planck units. A Planck length is about 1.6 times 10 to the minus 35 meters, incomprehensibly small. But the area of a horizon measured in these tiny Planck squares is a huge number. For a solar mass black hole, the entropy is about 10 to the 77th. That's a 1 followed by 77 zeros. For comparison, the total entropy of the sun itself, all its thermal energy, all its radiation, all its internal disorder, is about 10 to the 58th. The black hole has roughly 10 to the 19th times more entropy. Now, entropy is a measure of hidden information. It counts the number of microscopic configurations, microstates, that are consistent with the macroscopic appearance. A high entropy means there are an enormous number of ways the microscopic details could be arranged while looking the same from outside. If a black hole has entropy, it has microstates. If it has microstates, there's a microscopic description. There's information in there. And if there's information, it has to go somewhere when the black hole evaporates. Think about that for a second. Hawking's own formula, the formula he derived, tells us the black hole is storing information. And yet his argument about radiation says the information is destroyed. Something doesn't add up. The second clue comes from a thought experiment I developed in the 1990s, drawing on ideas from Gerard 't Hooft. Imagine you're watching someone fall into a black hole from a safe distance. What do you see? You see them approach the horizon, slow down due to gravitational time dilation, redshift, dim, and fade. They never quite cross the horizon from your perspective. They get smeared across the horizon like a film of paint. Their information, everything about them, appears to be encoded on the two-dimensional surface of the horizon. It's not lost. It's not inside the black hole. It's on the boundary. This led me to propose the holographic principle in 1995. All the information contained in a region of space can be described by a theory living on the boundary of that region. The maximum amount of information, the maximum entropy, is not proportional to the volume, as you might naively expect, but to the surface area. This is bizarre. It's as if the three-dimensional world we experience is in some deep sense a projection of information encoded on a two-dimensional surface. Like a hologram. I know what you're thinking. That sounds like science fiction. But it isn't. In 1997, Juan Maldacena, then a young physicist at Harvard, provided the most concrete realization of the holographic principle. He showed that a specific theory of gravity in a five-dimensional space-time, what we call anti-de Sitter space, is exactly equivalent to a quantum field theory living on its four-dimensional boundary. This is called the ADS-CFT correspondence. Exactly equivalent, not approximately, not metaphorically, mathematically identical. Every calculation you can do on one side, you can translate to the other. And the boundary theory is manifestly unitary. It's an ordinary quantum field theory. Information is conserved, period. Now, here's the key move. In the boundary theory, there's no black hole interior. There's no place for information to get lost. The black hole, as seen from the boundary, is just a complicated, hot, scrambled mess of quantum fields. It looks thermal, the same way a burning book looks thermal. But the information is there, encoded in the correlations between the emitted particles. When the black hole evaporates in the gravitational description, it corresponds to a perfectly unitary process in the boundary theory. Nothing is destroyed. The information comes out. It's subtle, it's scrambled beyond any practical ability to reconstruct, but it's there. Let me be very precise about this. Scrambled is the key word. When a black hole absorbs information and then radiates it back, it doesn't send it back neatly. It scrambles it. The information about your encyclopedia, your piano, your cat, it gets mixed up, spread across the Hawking radiation in extraordinarily complex correlations between billions upon billions of particles. In 2007, Patrick Hayden and John Preskill showed that black holes are, in a precise technical sense, the fastest scramblers in nature. They scramble information in a time proportional to the logarithm of their entropy. For a solar mass black hole, that's roughly a millisecond. A millisecond to scramble 10 to the 77th bits of information. Nothing else in physics comes close. But, and this is the part that still keeps me up at night, scrambled does not mean destroyed. A scrambled egg still contains every molecule of the original egg. You can't unscramble it in practice, but in principle, the information is all there. The laws of physics are reversible. Unitarity holds. Let me address the obvious objection. Someone will say, but Susskind, you're relying on the ADS-CFT correspondence, and our universe isn't anti-de Sitter space. Our universe has a positive cosmological constant. It's de Sitter, not anti-de Sitter. And yes, that's obviously true. We don't have a precise holographic dictionary for de Sitter space. That's one of the great open problems in theoretical physics. I've been working on it, so has everyone else. But here's why I still believe information is conserved. It's not just ADS-CFT. It's the accumulated weight of evidence from multiple directions. It's the Bekenstein-Hawking entropy, which tells us black holes have microstates. It's the success of string theory in counting those microstates. Andrew Strominger and Qumran Vafa showed in 1996 that for certain extremal black holes, you can count the microstates in string theory and get exactly the Bekenstein-Hawking entropy. Exactly, not approximately, the number comes out right. It's 't Hooft's S-matrix arguments. It's the Page curve. Don Page showed in 1993 that if information is conserved, the entanglement entropy of the Hawking radiation should follow a specific curve. It rises, reaches a maximum at the so-called Page time, roughly when the black hole has lost half its entropy, and then decreases back to zero. For decades, nobody could derive the Page curve from gravitational physics. Then, in 2019, a group of researchers, Ahmed Almairi, Netta Engelhardt, Donald Maroff, and Henry Maxfield, along with Jeff Pennington, showed, using a remarkable new tool called the quantum extremal surface prescription, and a technique involving what are called replica wormholes, that gravitational path integrals actually reproduce the Page curve. This was a breakthrough. The gravitational calculation itself tells you information comes out. Let me say that again, because I want it to land. The very equations of gravity, Einstein's equations, properly understood in a quantum context, predict that information is not destroyed. Hawking's original calculation was incomplete. It missed subtle gravitational effects that become important at late times, effects that reroute the information back into the radiation. The universe is self-consistent. Unitarity survives. Now, could I be wrong? Of course, I've been wrong before. Every physicist has. Lord Kelvin calculated that the Earth was at most 40 million years old because he didn't know about nuclear energy. Rutherford said in 1933 that nuclear energy was moonshine. History is full of confident physicists who were confidently wrong. But here's why I think this case is different. Those earlier mistakes were based on incomplete knowledge of the underlying physics. Kelvin didn't know about radioactivity. Rutherford didn't foresee chain reactions. In the black hole information problem, the evidence has been converging from completely independent directions: thermodynamics, string theory, holography, quantum information theory, gravitational path integrals, and it all points the same way. Information survives. That's not one argument. That's half a dozen arguments from different branches of physics, all giving the same answer. Could there be some dramatic revision of quantum mechanics that allows information destruction? In principle, yes, but that revision would have to explain why the ADS-CFT correspondence works, why the Bekenstein-Hawking entropy counts real microstates, why the Page curve comes out right, and why every experiment we've ever done is consistent with unitarity. That's a lot to explain away. Betting against unitarity is betting against the most battle-tested principle in all of physics. I wouldn't take that bet. And there's something deeper here, something philosophical, if you'll allow me that. The information paradox, the argument between me and Stephen, and between various camps of physicists over the last 50 years, was never really about black holes. Black holes were the stage. The real drama was about the relationship between gravity and quantum mechanics. These are the two great pillars of 20th century physics, and they don't fit together easily. General relativity describes space-time as a smooth, curved geometry. Quantum mechanics describes the world in terms of probabilities and discrete states and entanglement. For most purposes, you can use one or the other and get away with it. But a black hole is where both matter. A black hole is where the curvature of space-time is extreme and quantum effects are inescapable. It's the crucible. And what we've learned, I believe, is that when gravity and quantum mechanics conflict, quantum mechanics wins. The geometry of space-time, the smooth picture Einstein gave us, is approximate. It emerges from something deeper, something quantum mechanical. The holographic principle suggests that space-time itself might be built from entanglement. Mark von Ramsdonck and others have argued that the connectivity of space-time, the fact that two regions of space are connected, is equivalent to quantum entanglement between the degrees of freedom in those regions. Cut the entanglement and space falls apart. That's a radical idea, and it's far from settled, but it's the direction the physics is pointing. When I was younger, I used to think of black holes as the ultimate destroyers, the cosmic garbage disposals. Throw something in and it's gone forever. It took me years, decades, to understand that the opposite is true. Black holes are not destroyers of information. They are the ultimate scramblers. They take information and mix it up so thoroughly that it looks random, looks thermal, looks like noise. But it isn't. Every bit is preserved. Every quantum state is accounted for. The universe keeps its books balanced. I find that remarkable. Not because it solves all our problems. It doesn't. We still don't have a complete theory of quantum gravity. We still can't describe the interior of a black hole in a way that satisfies everyone. The firewall debate, started by Amheri, Marolf, Polchinski, and Sully in 2012, showed that there are still deep puzzles about what an observer falling through the horizon actually experiences. These questions are very much alive. But the big question, does physics destroy information? I believe the answer is no. And I believe this not because I want it to be true, but because the mathematics, developed by many brilliant people over many decades, keeps telling us the same thing. Unitarity holds. The laws of quantum mechanics are inviolable. Not even a black hole, the most extreme object in the universe, with a gravitational pull that traps light itself, can destroy a single bit of quantum information. The universe is more careful with information than we are. Think about that for a second. We lose our keys. We forget names. We accidentally delete files. But the universe, at the deepest level, never loses anything. Every interaction, every collision, every quantum fluctuation is recorded in the state of the universe, and in principle, it can always be read back. The past is never truly erased. Some people find this reassuring. Some people find it unsettling. I find it beautiful. After 50 years of listening to what physics says, I've learned to trust it, even when it tells me things I didn't expect, especially when it tells me things I didn't expect. That's what makes physics exciting. After all these centuries, the universe can still surprise us with the deepest things. Thank you for listening. I hope the universe has a few more surprises left. I suspect it does.